Hello everyone, welcome to NPTEL online course on electric vehicles. So in today's interaction, we will discuss the next topic under vehicle dynamics, which is simulation of dynamic equations with variable tractive effort. So in our previous interaction, we have derived different dynamic equations pertaining to variable tractive effort input to the vehicle. So let us try to see simulation of those dynamic equations in today's interaction. So as we have discussed, an EV works on three modes of operation. So these modes of operations are divided based on the speed of the vehicle. So when the vehicle velocity is between 0 and rated conditions, it is known as constant torque region, and when the vehicle velocity is between the rated velocity and the maximum velocity, the region is known as constant power region, and the speed operation greater than omega m max, it is known as constant speed region. So if we see the torque graph, so torque graph is this one. So torque will be equal to T rated in constant torque region, and we will look for maximum acceleration in this region. When the speed of the vehicle reaches the rated value, the machine will reach its rated conditions, and therefore the further acceleration is possible as a inverse function of vehicle velocity. So torque will be function of P rated by vehicle velocity. So this is the torque equation in constant power region. In constant speed region, there is no accelerating force required, and therefore the torque requirement is only to support the resistive forces and other losses due to transmission system. Now let us see the graph of power. So this is the graph of power. So power will vary in direct proportional to velocity in constant torque region. So since the torque is constant, power is directly proportional to velocity, and it will increase linearly, and it will reach its rated value when the speed reaches its rated value. So P is proportional to V in constant torque region. In constant power region, the P will be equal to P rated, and in constant speed region, the power requirement is only to support losses. So this is a quick recap of our discussion we have done yesterday. So we know that constant torque region operates when the vehicle velocity is between 0 and V rated, and the torque is proportional to or equal to T rated. So in this dV by dt equation, we generally substitute Tm equal to T rated and derive the dV by dt equation, which is this. In constant power mode, the vehicle velocity varies between V rated and V max, and torque will vary as inverse proportional to P rated by vehicle velocity. So therefore the torque proportional to P rated by V will be substituted here, and we will get a dV by dt equation which is this. And we can now see that we have an additional term here, which is K3 by V in comparison to the equation of dV by dt in constant torque mode. In constant speed mode, as the name suggests, dV by dt is equal to 0. So, there is no acceleration, and the torque and the power is only required to support the losses due to resistive forces and transmission system. So, the equation of torque will be just addition of all the resistive forces. So, we have also seen that it is possible to get very simplified equation for calculation of various performance parameters if we just ignore the load forces and inertial forces. And we were able to see that in constant torque region, so the velocity is between 0 and rated, torque is T rated. So, the time required to reach the vehicle to V rated speed is this equation. So, this is a simplified equation when we ignore the load forces. Similarly, since we know that the power variation is proportional to V, the average of power can be calculated as P rated by 2 in constant torque mode. We have also seen that the energy required, which is simply a product of P average into the time elapsed. So, it will be this equation. In constant power region, the vehicle velocity is between V max and V rated, and torque is proportional to P rated by velocity. So, if we do that, we can calculate the time elapsed, the time the vehicle takes to operate between V rated and V max is equal to TCP equal to this equation. So, and we also know that the power is constant in this region. So, therefore, the average power is same as rated power. So, if you want to calculate the energy that is required to operate the vehicle between V rated and V max velocities, the energy will be just P rated by TCP. So, these equations will be used to get approximate values of performance parameters. So, let us quickly see some analytical calculations that what we have just seen, and see whether they can be used to get reasonable values with respect to real time simulation. So, again let us take a vehicle, let us say take a battery electric vehicle with a variable input motor torque. So, gear ratio let us take as 10, radius 0.2 meters, mu RR 0.01, drag coefficient 0.26, frontal area of 2.2 meter square, mass of 800 kgs, and similar to last approximation, let us take the mass equivalent to the inertial force is equal to 5% of this mass. So, it is 0.05 m, efficiency of the gear is 0.9, rho is 1.25 kg meter cube, T max let us take as 80 Newton meter. So, in comparison to the last example we have taken, the mass is now reduced from 1200 kgs to 800 kgs, and T max has increased from 40 Newton meter to 80 Newton meter. So, since we are simulating a variable input motor torque conditions, we have to define the rated vehicle velocity. So, let us take 50 meter per second as rated vehicle velocity, which turn out to be 180 kilometer per hour speed. Also, let us take the maximum velocity of the vehicle equal to 70 meter per second, which turns out to be 252 kilometer per hour. Also, let us assume the slope is 0 and the wind velocity is also 0 to start with. So, once we define the parameters and their values, we can now start calculating the different forces. So, tractive effort is this equation G by R T max in the efficiency gear, it will be 3600 Newton. Rolling resistance force will be equal to 82.40 Newton. Gradient is 0 because there is no slope involved. The constant term of the aerodynamic force, which is 0.5 rho AR into CD, it is 0.3575. Now, we have to calculate three constants. So, K1, K2 and K3. So, K1 is FTE minus FFR by minus Fg by total mass. So, it is 4.256 into 10 raised to minus 4 meter per second square. Constant K2 comes out to be 4.187 and the unit is 1 by meters. Constant K3, which is a new constant in this mode. So, K3 comes out to be 192.85 Newton meter per kg second. So, once we have all these calculations with us, we can calculate the different performance parameters. So, we know that if we do exact calculations based on the equations we have derived for constant tractive inferred input, we can do so. So, the time, so we know that in constant torque mode the Vf is equal to V rated. So, if we know this, we can substitute it in the time equation and we can get the time that is required to bring the vehicle from 0 speed to V rated speed. So, we know this equation and it turns out to be 13.14 seconds. Similarly, if you substitute this time in the distance equation, we can again get the distance that the vehicle travels when the vehicle moves from 0 to V rated speed is equal to 0.344 kilometers. So, again let us try to calculate the average power that is required in the constant torque region. So, if we substitute the required values of force, constants and time elapsed, we can see that the average power in constant torque region is 94.34. And the energy required by the battery will be product of P average into time in constant torque region, which is comes to 0.344 kilowatt hour. So, now let us try to plot the different parameters such as velocity, torque, distance. Since we know the equation of velocity with respect to time, distance with respect to time and also the torque variation with respect to different vehicle speeds. So, if you do the MATLAB simulation, we will be able to plot these graphs. So, let us see the variation of the torque input we are supposed to give when the vehicle speed moves from 0 to V rated to V max and the speed beyond Vmax. So, we know that in constant torque region, we generally keep the value of tractive effort or the motoring torque as constant. So, in our example which we have taken, we have kept T rated equal to 80 Newton meter. So, you can see that so the vehicle is operating in constant torque region here. So, of 80 Newton meter. So, this is basically T rated, and we can see that. So, this region is basically constant torque region. So, typically the time required for the vehicle speed to vary from 0 to rated condition turns out to be somewhere here. So, it will somewhere around 13. So, our calculation shows TCT equal to 13.14 seconds. So, it is coming as per calculation. So, once the vehicle reaches its rated velocity, we go for constant power mode, where the torque variation will be inversely proportional to vehicle velocity. So, we can see that that is happening. So, here torque is proportional to 1 by vehicle velocity. So, this region of operation is known as constant power region. So, typically the time required is probably around 27 seconds. So, when we reach, so in 27 seconds the vehicle will reach its maximum velocity of 70 meter per second or 252 kilometer per second. So, once we reach the maximum velocity, we will go for constant speed region. So, the torque required will be equal to the resistive forces. So, if we see the variation of velocity with respect to time for this variation of vehicle velocity, we can see that. So, we know that the constant torque mode is somewhere up to TCT equal to 13.12 seconds. So, you can see that roughly up to this speed. So, we will be in. So, we know that so this is we know that so V rated is equal to 180 kilometer per hour or 50 meter per second. And when we will reach we will start this constant speed mode when the time is around 27 seconds. So, we can see that it has reached its value of 252 kilometer per hour or 70 meter per second. So, this is V max. So, this is V rated and this is V max, and you have a constant velocity of 252 post 27 seconds. So, if we see the distance curve with respect to time, we can calculate the distance that is travelled. So, as per our calculations, we have calculated a distance travelled of 0.35 kilometers in TCD mode or constant torque mode. So, constant torque mode of so it is around this 13.14 seconds. So, we have distance equal to 0.34 kilometers. So, this is distance in kilometers. So, also in the velocity graph we can see that the acceleration between 0 to V rated is faster compared to the acceleration what we have from V rated to V max. So, this is understandable. So, acceleration is quite high and is almost linear, and it reduces in constant power region as a function of speed. So, it becomes lesser and lesser, it becomes and then becomes 0. So, this can be observed from the velocity graph. Also, we can see that the distance which the vehicle travels is on time proportional to 27 seconds will be somewhere around 1.3 kilometers in the constant power mode. So, we have also seen the method of calculating this performance parameter by some approximation, such as neglecting resistive forces and other losses. So, in constant torque region or constant torque mode, we can calculate the approximate value of time elapsed as this equation, which gives the time equal to 11.66, but the exact timing is 13.14 second. And the power calculation, if we see the average power calculation, comes out to be 100 kilowatt, but the exact calculation shows it is 94.34 kilowatt. So, it is basically under 10% accuracy, you can say. The energy calculation with the approximations comes out to be 0.324 kilowatt hour, but on the exact calculation it was 0.344 kilowatt hours. So, to check these approximations with respect to the simulation, we can do another simulation where, while plotting the velocity, distance and the torque plot, we will neglect the losses. So, if we do that, these approximate values should match with the simulation values. So, the approximate values of time, average power and energy required in constant power region with this approximation comes out to be TCP of 5.6 seconds, but in actual exact graph we have seen it is 27 minus 13.14. So, which comes out to be around 14 seconds. So, this approximation is not good and it has lot of errors, quite reasonable error. The average power required in constant power mode is 200 kilowatt and the energy required will be 0.311 kilowatt hours. So, let us try to do the simulation with this approximation where we actually neglect the losses due to resistive forces like rolling resistance, aerodynamic resistance, slope, and all the transmission losses. If we do that, this value should meet the simulation. So, let us see the graph of velocity with respect to time. So, the bold graph is the exact graph that we have seen just some time back, and this dotted graph is the approximate graph of velocity with respect to time. So, you can see that the velocity comes to 0 in constant speed mode. Why it is so? Because there is no resistive forces and there is also no aerodynamic force which was proportional to speed. So, the torque requirement will be totally 0. So, this kind of validates the approximate nature of this velocity variation. So, this is basically exact graph, and this is basically approximate variation of velocity with respect to time. So, we can see that the time required for the approximate curve is 11.66. So, this is equal to our calculation of TCT in approximation. So, it is coming as per the calculation. Similarly, the TCP is coming roughly as 5.6 seconds, which is again meeting the calculations. So, our calculations can be also validated using this kind of graph. But we can see that the approximation and the exact curves are quite not matching, especially in constant power mode and constant speed mode. So, it shows that the effect of resistive forces such as rolling resistance force, gradient force, and force due to aerodynamic drag force cannot be neglected for approximations. We can also see the variation of velocity with respect to time for both exact curve and, so this is exact curve and this is approx. So, approx is basically shown in dotted curves. So, again we can see that here the constant speed mode starts very early compared to the exact mode. So, why it is so? Because the system is able to accelerate very fast, because it does not have to support now the resistive forces. So, we have seen that the constant speed mode starts somewhere around 17 seconds, while the for the approximate while actually it starts at around 27. So, 27 seconds for exact curve. Similarly, if we see the distance variation of the vehicle with respect to time, so the variation is not very high, and it is only in terms of few hundred meters. So, at the end of constant power region, which is around 27 seconds. So, you can see the error is basically you can say maybe 200 meters. So, this is the error in distance at vehicle velocity equal to V max. Now, let us try to quickly see all this variation, this velocity variation with respect to time, distance with respect to time, and torque variation with respect to time in a same graph. So, where we can appreciate the variations. So, basically so this is basically constant torque region. This is constant power region and this is constant speed region. We can also combine the approximate variation also in the same graph as exact graphs. So, you can see that the constant power region is very low in comparison to constant power region of the exact curve. So, once we have the simulation with us with exact variation of velocity with respect to time, distance with respect to time, as well as torque variation with respect to time, we can do some performance analysis for different kind of conditions. So, let us say if we assume that the vehicle is driving on a slope of constant 5 degrees, then what will be the vehicle performance in different regions of operation. So, again this will be plotted in dotted curves. So, this is exact curve and this is the condition of with slope equal to 0 and this is with slope equal to 5 degrees. So, we can understand that if there is a slope, we now have a gradient force also to cater, and therefore, the acceleration has become slower compared to the case where the slope is 0 degrees. And we can also see that since the acceleration has become slower, it will take more time to reach the rated speed. So, rated speed is reaching at around 17. So, this is the TCT for 5 degree slope and this is TCT for 0 degree slope. So, the constant torque region has become more because of the low acceleration due to slope. We can also see the variation in performance of the system when the mass is reduced from 800 kgs to 600 kgs. So, if we reduce the mass of the vehicle, we expect a faster acceleration. So, we can see that also in that graph. So, this is basically the case where mass is 600 and this is mass is equal to 800 kgs. So, when we reduce the mass, the acceleration becomes faster and we can reach the V max velocity earlier. So, you can see that the V max is reached in, so this TCP for 600 kgs is around 20 seconds, and it is TCP for 800 kgs mass. The system is able to accelerate fast. So, this was some of the performance checks you can do when the simulation is with us. Now, let us try to see the kind of simulation files. So, if you want to simulate in MATLAB, basically in .m file, we can do this kind of parameter definition and allocating values, very similar to what we have seen in the analytical calculations. So, we will just put all the values of gear, radius, mu RR, CD, AR, mass, efficiency of gear, rho, T max. So, this is basically 80. So, 80 Newton meter, VC of 50 meter per second and 70 meter per second. We know that 50 meter per second means 180 kilometer per hour, and 70 meter per second is 252 kilometer per hour. Oh, sorry, the mass is basically 800 kgs in this case. So, as I said, the mass is 800 kgs and the torque is 80 Newton meter. Once we define the parameters and the variables, we can start with the calculations of forces. So, we can calculate the tractive effort, rolling resistance force, gradient force, and the constant term of the aerodynamic force. And so, once we have this all forces and constants with us, we can calculate the k constants. So, k1, k2, k3, and we have a new constant which is k2a. So, k2 which is FTE minus FR minus FG by m1 in. So, this is constant torque region k2, and this is basically k2 for a constant power region. So, k1 is constant for both this thing, but k2 is different for constant torque and constant power region, and k3 only comes into picture in constant power region. So, once we have defined and the variables and calculated the basic forces and the constants, we can write the actual for loop. So, as we have seen in previous simulation file, we have to define the arrays. So, in this case, since the TCT is around 13 seconds and TCP is around 27 seconds. So, we thought it is reasonable to do the simulation for 40 seconds and with a time step of 0.1 seconds. So, dt is 0.1. So, we have to define velocity array, distance array, torque array, and so we will simulate for 400 array number, since 40 second with time step of 0.1 means 400 cycles. So, we have 3 regions to simulate. So, we have to simulate constant torque region, the equation is different. In constant power region, the equation is different. So, we have different equations for constant torque, constant power and constant speed. So, when the vehicle velocity is less than Vc, so Vc is our V rated. So, when the velocity of the vehicle is less than V rated, we have to write the equation pertaining to constant torque region. So, this is constant torque region velocity equation in terms of Vn plus 1 and Vn. and the torque will be constant. So, Ft is constant and torque will be equal to T rated. So, this calculation has to be done in constant torque region. When the velocity of the vehicle is greater than Vc max, we basically are in constant speed region. So, the speed will be constant and there is no acceleration. So, torque is equal to just all the losses. Else means the condition where V in is between V max and V rated. So, this is basically a constant power region. So, where we have to write the velocity equation in terms of K3, K2A and K1, and the torque will be inversely proportional to vehicle velocity. So, all these regions we have to define and they will be toggled with respect to the variation of vehicle velocity. So, when we are less than V rated, it is constant torque. When we are between rated and max, we are in constant power mode, and beyond V max we are in constant speed mode. We can also calculate the distance as we have done in the case of constant Ft. So, once the whole program is written, we can plot this using simple plots. We can label them and put a proper axis so that the clarity of the graph is maintained. So, this is the end of the discussion under the topic dynamic equation simulation with variable FTE. Now, let us go to the next topic which is understanding of different driving cycles and range. So, range calculation is very critical and important in EV application, because we have a limited energy that can be stored in batteries. So, what are the different methods of estimating ranges, and also comparing different vehicles. So, one is constant speed test. We operate the vehicle in constant speed and try to understand the range. So, this method is very straightforward, but it is not a realistic one, because a typical vehicle will not operate in constant speed mode all the time. So, the practical condition is, or the realistic condition is, varying speed. So, we do mostly varying speed test to test the range of a vehicle. So, we have to define different driving conditions and profiles. So, we have profiles for urban transport, profiles for highway driving. We can have profiles for hill type of terrain, etc. So, this kind of test is complex, but it is useful and can be applied for vehicle range performance testing. So, driving cycles is one of the ways to test the range. So, different regulation agencies have defined standard drive profiles. Means they will define graphs of velocity with respect to time. So, it can be any variation. So, this and so vehicle range estimation will be done based on this different kind of profiles. So, this range calculation will be used to benchmark and even compare the fuel economy as well as emissions of the vehicle. So, it has multiple purposes. So, in United States there is an agency called EPA, this is Environmental Protection Agency. So, it has defined various kind of driving cycles profiles. So, FUDS which is Federal Urban Driving Schedule, this is Federal Highway Driving Schedule, this is high energy and fuel efficiency kind of graphs. In Europe we have curves or driving cycles such as EC15, EC47. In Japan there is a driving profile which is SAE J227 and it has all the variation A, B, C, D based on the different time that is involved. In India also the agency known as ARI which is basically in Pune. So, it is Automotive Research Association of India. So, it defines a lot of profiles for Indian urban and highway driving conditions. So, let us see some of these driving profiles. So, in FUDS basically this kind of variation of speed versus time is given. So, it is basically for 1500 seconds. So, it has a very high variation of speed with respect to time. So, this is a typical basically urban kind of transport where you have frequent start stops. So, let us see the driving profile of a HFET driving profile. So, it is highway fuel economy test schedule. So, we can see that the variation is not high here and mostly you are operating at higher speeds most of the time. There is another driving cycle which is known as US06. So, it takes care of highway conditions and even some of urban conditions, and it has very high variation of dV by dt. So, this acceleration is very high. So, it is quite a rigorous driving cycle as per vehicle performance is concerned. So, this is a European driving cycle which is known as EC15. So, this driving cycle mostly have very simple driving profiles. So, it has constant acceleration period, constant velocity period and constant deceleration period. So, it has different magnitudes. So, so this acceleration is for less time, this acceleration is for more time, this acceleration is for still more time. So, such kind of variations are defined to test the vehicle range performance. So, we have talked about a driving cycle which is known as SAE J227. So, in this a driving cycle will be constructed as an addition of different acceleration and constant speed. So, we can see that you have a acceleration period which is defined as T acceleration. We have a high speed cruising for period of T cruising, a deceleration or T braking here, a idling period of where there is no speed, and there is a coasting. So, T coasting is a period where the tractive effort is reduced to 0. So, it is a kind of vehicle is floating on inertia and road conditions. So, different variation of this SAE is available in terms of J2 to 227 A 227B, where this different time such as T acceleration, T cruising are are varied for different ABC. So, how to calculate the range of a vehicle? So, when we want to calculate the range of the vehicle, the first thing we have to define is the driving profile. So, this is the first thing. On what driving conditions you are checking the range. Secondly, what is the battery capacity? So, these two things are important to start with. So, these two things should be known initially. Afterwards, for this driving profile, so which is a basically variation of velocity with respect to time, you have acceleration, deceleration, constant speed, etc. The vehicle tractive effort and velocity will be known to us, and we can calculate the power that is required by the vehicle in a time span. So, this all are a function of time. So, once we know the efficiencies of gear and transmission, we can calculate the power that is required on the motor shaft. Similarly, when we know the efficiency of motor and power converter, we can know the power required at the input of the power converter. We also have power required for different accessories that are basically steering, AC and other loads. So, this has to be added to accessory loads, and together we can get the battery power. So, this all things can be calculated as a function of time once we know the driving profile. So, if we have the P battery available, we can calculate the average. So, P battery average can be calculated. Once we know that and the total time elapsed, we can calculate the energy that is required from the battery. So, you can see that when we are operating the vehicle on a driving profile, the vehicle will run as long as the energy required by the vehicle is equal to the energy stored in the battery. So, once the battery energy is all exhausted, vehicle has to come to rest, and the distance travelled in this duration is the range. So, it is very straightforward. So, this calculation goes as long as the battery capacity comes below a threshold level, where we say that we cannot supply any more energy. So, the distance travelled is the range. So, let us see the algorithm we do for range calculation. It is a time step simulation. So, we have to model all the systems. So, we have to model the transmission system, we have to model the gears, we have to model the motor, we have to model the power converter, and even the power required for the accessories. So, we have to have all these models with us. So, we will start with a battery with a certain SOC, then we will load the driving profile data. So, for each variation of velocity versus time, we can calculate the distance, it is speed into time. Then we have to calculate tractive effort, and we have to take care of all kind of efficiencies of different systems. like a gear, transmission, motor, power converter and the power due to accessories. If you have that, we know the total power that is drawn from the battery. Once we know that, we can calculate the P battery average and calculate the energy required. So, we have to subtract the energy required, that is delta energy, from the energy initial. So, we have to E initial minus delta E we have to do. So, once this becomes negative, we have to stop this simulation. So, subtract from the available storage, and if SOC is greater than threshold, we can redo the calculations, and we have to stop where the E final, which is E initial minus del E, becomes negative. So, there we have to stop the simulation. So, that is all for today's interaction, and we will continue discussion on the topic of vehicle dynamics in our next interaction. So, thank you for listening the lecture.